How to write code for matrix chain multiplication. In the last two lectures, we learned about matrix chain multiplication problem and the algorithm that can be used to solve this problem. Here, we are going to see how can you write code in order to solve this problem. We already know the algorithm. We want to see how can you write code for this. Again, I want to emphasize that the problem of matrix chain multiplication is not about finding the result of matrix chain multiplication. Instead, it is about finding the right way to parenthesize matrices such that the result is obtained with minimum number of scalar operations. When you have a lot of matrices in the chain, let us say A1, A2, A3 and so on, A4 and so on, there are many possibilities of parenthesizing this. That is, first you can multiply A1 with A2, then that result with A3, that result with A4 and so on. Or it can be first you multiply A1 with A2 and then multiply A3 with A4. Then you multiply these two results. This is also possible. So when you have a chain of matrices, there are a lot of such parenthesizations possible. And you want to find out which parenthesization helps you find the final answer with least number of scalar operations. Keep in mind that whatever be the order in which you parenthesize, final result of matrix chain multiplication will always be same. The only question is how many scalar multiplications do you want to perform in order to get the final result. Let us get into what we learned in the last lecture and how to convert it into code. In the last lecture, we learned about the algorithm. What did we learn? First, you have to have a DP table. DP table should be having values, let us say, any particular entry dpij. This will represent minimum number of scalar multiplications needed to compute the product of matrices. That is matrices from AI to AJ. I'm not explaining because in the last lecture, we already went in detail. Then you had a base case. dp of ij is equal to 0. After that, you had a recurrence relation. Again, I'm not getting into the details. I'm just writing the recurrence relation because we already discussed and we want this base in order to discuss this lecture. That is how to convert this thing into a code. That is what we are discussing here. dpij is equal to, what did we learn? It should be minimum of all the values of k between I and j such that dp of, what is the first split? dp of I, k, that is all the matrices from the ith position to the kth position, plus what is the second part of the split? dp of k plus 1 to j, plus what is the third component here? It is when you already have these results, that is I to k are already multiplied, you have this result here. K plus 1 to j are already multiplied, you have the result here. Then you have to include the additional computation that should be done in order to multiply these two matrices, because you have these two as the result and you have to multiply these two. How will you multiply? That total number of scalar operations required will be pi minus 1 into pk into pj. This is what we learned in the last lecture. What we are going to do now is, after this you already know the final answer that will be present in dp of 1n. So for each of the entries in the matrix, you have to use these formulas and you want to update each entry starting with the diagonal elements. So diagonal elements will be anyway 0. Even if you don't update, it's okay. After that, you will update these ones, then these ones and so on. Finally, you will enter this one. Whatever is the top right corner entry, dp of 1n. This is the final answer that you're having. So let us see how can you write code for this. This part we'll go slowly, we'll explain in detail. Previous part I went fastly because already we discussed it in the last two lectures. We are getting to the code. Let us say we want to write a function called as matrix chain multiplication. We'll call it MCM. What is the input? Input is an array called as P. Why am I calling this P? I'm calling this P because this P array will have entries P0, P1, P2, P3 and so on. What are these P's? These P's will tell you what is the dimension of each matrix. First matrix A0 will be having dimension P0 cross P1. Second matrix A1 will be having dimension P1 cross P2. Third matrix A2 will be having dimension P2 cross P3. This is how it goes. That is why you will have a matrix P which will just have the dimension of all the arrays possible. That is P0, P1 up to Pn. This will give you dimension of all matrices. Okay. So this matrix will be of size n plus 1 because it starts from P0 and goes till Pn. So how many matrices will this include? N plus 1 dimensions will give you information about n matrices, right? Because P0 by P1 is corresponding to one matrix, P1 by P2 is corresponding to next matrix and so on. So n minus 1 P's will give you dimensions of n matrices, right? So now you have dimensions of n matrices with you. What is the first thing you want to know? You want to know what is n? What is the number of matrices you are having? So that n, this will be equal to whatever is the length of your array P minus 1. Because we already discussed if the length of P is n plus 1, then the number of matrices is n, right? So your n is length of P minus 1. Next thing is, you want to declare a DP table, the dynamic programming table. What should be the size of your DP table? Dynamic programming table. It should be n cross n. So n cross n matrix. This matrix will be initialized with all zeros. Okay. All the values will be zeros to begin with. It is an n cross n matrix. What is the next step? Next step is, at this point you have the matrix. This is an n cross n matrix. You have to start filling this matrix. This is the next step. What did we learn? We should first fill the diagonal elements, then the next diagonal, next one. Finally you will reach here, right? First you should fill the main diagonal. But the point is, in the main diagonal, it represents the values dp, 0, 0, 1, 1 and so on. What are these? These are all single matrices. There is no multiplication to be done because this includes only one matrix. This also includes only one matrix and so on. Because of that, you know the total number of scalar multiplications required in all these are 0. So all your diagonal elements will be 0. That means you can start from the length of 2. That is, for multiplying at least you need 2 matrices. So the outer loop will run for the length of the chain. Let us say for the length of chain L is equal to, you will start from 2, or I'll put a capital N, L. For L is equal to, from 2 to what is the total number of matrices you have? N. So you are filling it progressively, starting from the length of 2, that is this diagonal. Then you will fill length of 3, finally length of 4, which is n here. So you are going to start with length of 2, you will go till n. What is the next factor in the loop? The inner loop should run for all the starting indices of the chain. So we'll call starting indices as I. For what should be the starting indices? From I, it can be from 1 to n minus, what should it be? N minus L is length. So n minus L plus 1. Till this point it can go. That is, if I am starting with 1, let us say length is presently 2, then this will be n minus 2 plus 1. This is how you should do. So for I equal to 1, 1 to n minus L plus 1, what is the next step? You should have the value of j. So this is the starting index. Next is the ending index. Ending index, I'll call it as j. J will be I. From I should go till the ending index. So let us say my I is 1. Length is 2. What should be the ending index? If my I is 1, that means I'll start from 1. What should be the ending index? I already know length is 2. So ending index should be 2. Then from 1 to 2, the length is 2. So this should be I plus L minus 1. Here you can put the values and compute. If my I is 1, that means 1 plus 2 minus 1, this will give you 2, right? This means the length is 2. So my first loop, the more outermost loop, this is going to tell me what is the length. The length means total length of the chain. Final one that I have to find is of n, but I'll start finding from 2 and I'll move on till n in order to find the final answer. The next loop, the inner loop, this loop will tell me what is the starting index. So initially my starting index will be 1, then I'll go till the last possible index with the given length. So that last possible index will be n minus L plus 1. Then the next thing is I have to say what is the ending index if any particular I is my starting index. So the ending index is I plus L minus 1. Now that you have both the ending index and starting index, dpij will tell me what is the value to be put there. Initially what will I do? I'll say my dp of ij, this is equal to infinity. When I write infinity, in reality you have to put a very large number. That is what it means. Okay? Because we want to find the smallest number possible. So initially you can populate a very large number. Then whenever a smaller number comes in, that will be substituted. What is the next step? Now for this dpij, let us say this ij is 2, 5. What do you want to do? You want to find all the possible splits in between, and among those splits you want to find out which is the one giving least number of scalar multiplications. How do you find all the splits? You have to again write a for loop. So this for loop, let us say for k is equal to, what can be the first point of split? Whatever is your starting index. K is equal to I to what is the last point of split? Last point is wherever it is ending. So j is where it is ending. So you can split till j minus 1. Okay. So your split can be from I to j minus 1. For each of those split, what should you do? You have to calculate the cost. How to calculate cost? That is where we wrote this formula. Using this formula, you can find out the cost when the split is at k. When the split is at k, you can compute dp of ik plus dp of k plus 1j and the cost of multiplying these two matrices. This matrix and this matrix. That cost is this. So already you have first matrix cost, second matrix cost, and the cost of multiplying first and second matrices. We'll write the same thing in another form here. K equal to I to j plus 1 for each of those. What is the cost? Let me call cost as C. My cost is equal to dp of I. What is the split? Split is at k. So dp of ik plus, what is the second part? dp of k plus 1 j. This is the second part. Plus, what is the cost? So already you understood what is first matrix, second matrix. That is the cost of computing, multiplying from I to k, cost of multiplying from k plus 1 to j. But now you have these two matrices. If you multiply these two matrices, for that the cost will be P of I minus 1, that is the starting index, into P of, second one is k is the split. So you have P of k into P of j. Where did I get this from? Where did I get this formula? This also I used this one that we learned in the algorithm. In the algorithm that we discussed, we had again explained what this is. So the same logic I'm using here. I'm just converting it into code. Okay. So once I have this, what is the next thing? Next thing is I know what is the cost when split is at k. Next step is to update this dp of ij. When will I update? If this cost is smaller than the already existing cost, that is when I will update. So how will I update here? My dp of ij, how will this be updated? This will be minimum of whatever is already existing. If that is the smaller, then you don't have to update, you just have to keep it. That is dp of ij or this particular cost you have calculated. Whichever is smaller, that will be stored in dp of ij. So once you complete this loop, that is for each of the length from here on, for each of the length, for each of the starting index, for each of the split, for all these conditions, if you complete the loop, finally you will have the final answer. Which will the final answer be? We already told this block, the top right corner block, this will be having the final answer. So that block will be dp of 1n. That is what we have mentioned there. So this will be final answer. You can say you can return dp of 1n. This is the final answer you are having. So we'll just go through this algorithm once more and then find out what are the time and space complexities here. This is the algorithm, matrix chain multiplication. First you are finding the length n, that is the length of matrix P minus 1, right? After that, the dp table, it should be of size n cross n and all values should be 0. We are putting all zeros so that diagonal elements we don't have to specifically update. It will anyway remain as 0. Then for each of the possible length of matrix from 2 to n, length 2 means this diagonal, length 3 means this diagonal, length 4 means next diagonal, so on. Here we only have till 4 in this picture, but it can be up to n. Then for each of the diagonal, how will you fill? For each of the length of the matrix chain, you have to find what is the starting index. For each of the starting index, you have to first find out the ending index. Once you're sure with ending index, you will initialize dpij, that particular column, with infinity. Infinity means a large number. That is what you can understand. Then for each of the split k possible between I and j, what do you want to do? You want to find the cost if split was done at this particular point. Then if this particular split gives you a cost that is smaller than the value already present in dpij, that means the best split is this k. That is what you are updating. So when you run this loop completely, you will know which is the best k that will give smallest possible value of dpij. That is the smallest possible number of scalar multiplications. Once you complete this loop till this point, then you will know what is the smallest value possible for each of the starting index for given length. Once all these loops are completed, then you will be sure what is the smallest possible scalar multiplications, count of scalar multiplications considering all the lengths. So you actually want to find for length equal to n, that is considering all the matrices in the chain. You want to find what is the minimum number of scalar multiplications to be done during matrix chain multiplication. So that is what this final value dp1n will have. The next question is, what are the time and space complexities of this algorithm? Coming to time complexity, let us say there are a total of n matrices that you want to multiply, that is a1, a2 up to an. These are the matrices. If this is the case, then what is the time complexity? So let us analyze these loops. In this algorithm, these are all order of 1 operations, so nothing to be done here. These are all order of 1. At this point, this loop is running from 2 to n, which means this is order of n times. Order of n times this outermost loop will be run. Next thing is, what about the next inner loop? So this outermost loop, this will be run order of n times. Next loop, this one, this is running from 1 till the last possible starting index. So this is again an order of n loop. So for each of the outer loop, this inner loop will run order of n times. So order of n times outer loop will run. For that, each of those n times, inner loop will run order of n times. So this will make a total of order of n square. So at this point, you know already it is running order of n square times. Then there is a additional inner loop here. This is running for every possible split between I and j. Here, if you think in the worst case, possible split have to be calculated for all the points from 1 to n. But there can be smaller cases when I and j are smaller values, anything in between. But in the worst case, from 1 to n, for everything you have to find out. Considering that the worst case number of times this particular loop, the innermost loop, has to be run as again order of n. So considering this, there is an outer loop which is running order of n times. For each of those order of n times, you may have to run this loop again order of n times, which accounts to order of n square. For each of those order of n square invocations, you have to run one more inner loop, which is running in the worst case in order of n time. That means order of n into order of n into order of n, a total time complexity of order of n cube. So that is why time complexity of matrix chain multiplication is order of n cube. Next question is, what is the space complexity? When we are considering space complexity, we'll only be looking at the additional space that is used. What is the additional space used here? For the DP table, you are making an n cross n table. So this means order of n square space is used for this DP table. So just because of this DP table, your space complexity will be order of n square. So the time complexity of matrix chain multiplication is order of n cube and space complexity is order of n square.